Transformers are the silent workhorses of our power systems, but a sudden internal fault can turn an expensive industrial asset into scrap metal in seconds. To prevent that, we are going to configure a specialized 3-part protection protocol designed specifically for a dry-type transformer. This requires a different approach than traditional utility transformers. Oil-filled units rely on these large overhead conservator tanks and gas detection relays to spot trouble. Dry-type units lack these oil-handling components entirely. Without insulating fluid or gas detectors to provide early warnings, our primary threat vectors narrow down to internal heat generation and direct electrical faults. Because dry-type units lack fluid cooling, configuring proactive, direct monitoring on the coils themselves is our only method to prevent total asset destruction. Step 1 is managing thermal stress. A transformer operates by isolating circuits and stepping voltage up or down across its primary and secondary windings. As electrical current passes through these solid copper or aluminum coils, it encounters natural resistance, which constantly generates heat. We calculate this heat using the I²R formula, where current and resistance dictate an unavoidable escalating thermal buildup. Without a liquid cooling bath to dissipate this energy, the physical paper and resin insulation wrapping the windings becomes the system's most vulnerable failure point. To defend against this, we configure the Winding Temperature Indicator, or WTI. We place fiber optic temperature sensors physically inside the dry coils to achieve direct, high-accuracy measurements that are immune to electromagnetic interference. We set our initial WTI alarm limit between 85 and 90 degrees Celsius. This provides an early warning to the control room if the load gets too heavy. Then, we set the critical WTI trip limit at 90 to 95 degrees Celsius. This is the absolute ceiling. If the coils hit this temperature, the relay forces a breaker trip to shut the system down. Configuring these strict limits provides our first line of defense against irreversible thermal damage to the winding insulation. With our thermal limit secured, we move to our second line of defense, mitigating electrical threats, specifically phase-to-phase faults, using overcurrent protection. Before we can set this relay, we have to calculate the transformer's full load current. This equation shows how we find that value. Rated power in kVA times 1000, divided by the square root of 3 times the rated voltage. For example, a 100 kVA transformer with an 11 kilovolt primary yields a full load current of 5.25 amps. A common mistake is setting the relay's pickup current exactly at this 100% mark. Setting it this low guarantees nuisance tripping. It fails to account for normal, harmless transient surges that occur when equipment powers on. Instead, the correct and safe pickup current threshold must be set between 125 and 150% of the full load current. We then apply an inverse time characteristic to this setting. This logic ensures that massive fault currents are cleared almost instantly, while smaller overcurrents are given a slight time delay. A mathematically precise overcurrent relay ignores standard operational spikes, but instantly isolates catastrophic short circuits before they destroy the windings. For large industrial units, typically those exceeding 5 megavolt amperes, we require a final, highest-tier layer of protection. This is differential protection. It is a logic system based entirely on real-time current comparison. This schematic shows how we place current transformers on both the primary and secondary sides of the unit. During normal operation, the differential relay continuously compares measurements from both sides, verifying they balance to exactly zero. If an internal winding fault occurs, current leaks within the system, instantly shifting that balance out of equilibrium. The differential relay detects this localized imbalance and immediately triggers a trip signal to the circuit breaker. Differential protection provides the fastest, most decisive isolation for internal faults. It cuts the power long before the extreme thermal and mechanical stress can cascade through the rest of the facility. We have now successfully implemented a complete 3-part protocol: thermal, overcurrent, and differential protection. What started as a highly vulnerable system is now a secured, robust asset. In its current operational state, this network of relays and sensors will detect abnormal conditions and isolate faulty equipment faster than you can blink. Understanding dry-type principles and applying these exact configurations turns a fragile machine into a resilient powerhouse. Next, we will coordinate this setup with restricted earth fault protection to cover the final blind spots.